on. You have other chances to discuss with the speaker. We have Serge talk from Subhankar from University of Minnesota.
Good morning. Can you hear me? Good morning. I'm Subhankar. I'm a computer science PhD candidate at the University of Minnesota. I'll be presenting a work on towards Kriging-informed conditional diffusion for regional sea level data downscaling on behalf of my co-authors, Arun, Jayant, Professor Shekhar, and Professor Subramanian. Okay. So the problem of downscaling is basically we want to derive how high resolution data from low resolution climate variables. And the coarse resolution variables can be from global climate models or even from satellite data. So basically, if you look at the figure to the right, most of the image actually shows, most of the map actually shows coarse resolution data. But if you look at the diagonal red strip, it shows high resolution data where you can see the climate, where you can see the spatial variability very clearly. So that's why it's very important for regional assessments, also to make like regional policies that we want to know the sea level or the climate variables very at fine scale. So the domain objective is we want to provide more accurate regional predictions from coarse resolution data of the climate variable. Uh, for our use case, we are mostly focusing on sea level data, but we also provide experiments on the eddy current energy, EK variable. So for the problem formulation, we have the input, which is basically the coarse resolution data that you see to the top left. And we have a model, which is the diffusion model, which will output the fine scale resolution data that we want to generate from the coarse resolution data. So basically, for input, we are taking a coarse resolution input of the climate variable. We have a diffusion model which processes the coarse resolution data to generate the fine scale resolution data, which will actually address and produce the spatial variability at a higher resolution. Our objective is we want higher solution quality and model generalization because we do not want our model to be working only for sea level data, but also for other climate variables. A constraint is that our model should learn the spatial variability and also should be adaptable to other domains. So some of the challenges, one of the major challenges is the complexity of the climate data, as well as the spatial and temporal dependencies, plus climate data is usually non-stationary across the temporal domain. For our contribution, we propose a Kriging-informed conditional diffusion probabilistic model, which integrates Kriging's spatial dependency capabilities, as well as the nonlinear relationships that can be provided by the conditional diffusion model. We also propose a variogram-based regularization, which ensures that the data that is being generated by the diffusion model adheres to the spatial variability of the ground truth data, or the spatial dependencies, you can also say. We compare our approach with state-of-the-art machine learning models, such as CNNs and GANs, and also we produce a case study. So for the limitations of the related work, if you look to the right, the table provides some of the recent works on downscaling. So one would be mostly like interpolation-based works, that would be the 4, 5, and 6. And the other would be primarily like machine learning-based works, 1, 2, and 3. So interpolation-based methods such as bilinear or bicubic interpolation would lead to very smooth outputs because they don't capture the nonlinear relationships very well. While machine learning methods, even if they can produce fine scale features, they usually do not consider the spatial dependencies explicitly. So what we want to do is to actually integrate both of them such that our output can produce fine scale features as well as consider the spatial dependencies explicitly. So this is a brief idea about what conditional diffusion probabilistic model is. So if you look to the right, the figure actually shows you what the pathway is. So if you have the forward process, which is represented by Q, the X0 is the ground truth, And at every step, what we do is add a small amount of Gaussian noise to the ground truth until it becomes at xt an isotropic Gaussian map, a map that can be considered an isotropic Gaussian noise. And in the reverse process, which is p theta, that actually represents the neural network, which wants to denoise the map that we have at the terminal step, that is the xt. And then we want to regenerate the ground truth from the isotropic Gaussian noise. And the neural network actually learns how to regenerate the data from complete noisy data, from a completely noisy map. So this is the forward process, and we have the reverse diffusion process. But what the training objective is, we are not exactly like comparing the data that is generated at each step with the ground truth. Instead, what the objective would be is to actually make an estimate of how much noise was added by the forward process at a specific time step. So if you're looking at a time step t, we want our model, that is p theta, to actually correctly estimate how much amount of noise was added in the forward process at that specific time step. And we want to minimize that. And that is what the variational lower bound actually represents. And the 1/t. So basically, we are taking an expectation over all the time steps for the amount of noise that was added in the forward process and how much was estimated by the model. So this is our proposed architecture. So if you look at xt, that was the terminal step, what was completely noisy map. And what we have is in our architecture, uh, so this specific reverse step, which is represented by p theta, at every intermediate step, we have a noisy map, which would be somewhat heading towards the ground truth with every step. But what we do is we also concatenate the output from the Kriging interpolation along the channel dimension, and that would actually give us, that would actually ensure that the network adheres to the spatial dependency knowledge that is offered by the Kriging model. So at each step, our network has a UNet, which is basically an encoder and a decoder structure. And if you look at the right, that basically represents one step of the diffusion model. So basically, what we have is at every step at the beginning, what we are taking in as input is the xt, which is the noisy map, and we are concatenating it with the output of the Kriging interpolation. And then at every step, we are also we are also concatenating the different scales of the output of the Kriging interpolation, because we want to ensure that the spatial dependencies are retained at different scales as well, and not just at only the topmost scale. And so this at the end of the UNet, that is the output, what happens is you get a comparatively finer out resolution of the input noisy map. And that's how, so this is just one step, and we run it for t number of steps, which for our experiments is 1000. Then we also introduce a variogram-based regularization. So if you look at this equation, that basically refers to the variogram of a specific image, of a specific map. So x0 over here represents the ground truth. And so the variogram gives you an estimate of the spatial dependencies of the different points in the map. And the modified loss function is basically, you just add the regularization term to the variational lower bound. And the RV is basically the difference between the variogram at a specific time step xt, that is the output by the model at a specific time xt, and the variogram of, and the empirical variogram of the ground truth data. And so by penalizing the RV value, we want to ensure that the model generates maps at every step, which adheres to the spatial dependencies offered by the ground truth data. For our experiment, we proposed the KICDPM model, and our main goal was to compare the solution quality offered by our model with other state-of-the-art models like CNNs or GANs, and most recently diffusion models. And our metrics were the root mean square error, the mean absolute error, the Pearson correlation coefficient, and for probabilistic error, CRPS. So these are some of the results that we would be looking at. So this is the coarse resolution input to the top. This is the coarse resolution input map for the sea level anomaly. It's the sea level anomaly variable. and that would be the ground truth data. And to the right is basically a table comparing our methods result or the output. And so this would actually give you an idea of what a baseline diffusion model produces, and this is what our model produces. So you can see, I'll show the difference map in the next slide. But if you look at to the right, show an ablation study of why the variogram-based regularization adds value to our model, and actually it improves the solution quality. So this is the difference map between the two of what the baseline diffusion model predicts and what our model predicts. So we can see that our model is comparatively closer to the ground truth than the baseline diffusion model. So we also tried our experiments on another climate variable, which was also in the same data set, the eddy kinetic energy. And again, these are some of the results, the qualitative and the quantitative results. Yeah, these are the difference maps. And as you can see in the EK variable as well, our model does better compared to the baseline diffusion model. For our future direction, we want to extend our experiments to other climate variables. And we also want to include physical constraints and try physics-informed models. We also want to try temporal downscaling and address the non-stationarity in the climate variable. We haven't yet addressed bias correction, which we plan to explore. And then there are methods to improve the computational efficiency in the reverse diffusion process, which we also want to explore. For acknowledgements, we are thankful to NSF, iHARP, our spatial computing group, NCAR, and MSI for the computing resources, and KMAT. Yeah, thank you.
Wonderful talk. Can you go back a couple of slides? One before, yes, right, this one. So as you look at the ground truth on the right side, you see some bumps in the ocean, right? In the sense that the values are not uniform. And a common sense would be that ocean should be a fixed level entirely, but obviously not, right?
So actually, this is not the difference between the model prediction.
Right, but in general, I mean, if you put the ground truth, it won't be the exact same level, right? Otherwise, no need to prediction. So I'm assuming, and perhaps the people here would tell, it must be because of the geology of the underground, right?
Yeah.
Ups and downs there. My question now is there a way to include that geographic features of the ocean in your framework?
Okay, yeah.
That would be very nice.
Yeah, that's true. Yeah, because we haven't actually considered the domain knowledge yet or the physics. Yeah. That's a very good point. Thank you.
Is there a question here? Oh.
Hi, it's very interesting talk. Can you talk about if the diffusion model, the output of your diffusion model satisfy, for example, mass conservation? And if so, how do you guarantee that? Or how do you impose mass conservation or like basic conservation laws in the model?
Yeah, thanks for the question. Actually, that's something we had been discussing before we submitted the paper, because yet we haven't considered any domain knowledge. And that's what we want to explore, whether it's the mass conservation or even the physics behind how we are working with it. But yet, yeah, that would be part of our future work, as you mentioned. And the mass conservation is one of the primary concepts that we'll be including the domain knowledge. Thank you.
Can you explain a little bit more on why do you think that Kriging-informed actually helped? Because sometimes people say the Kriging does not help their particular regions and physics processes. What's the reason do you think this one helps?
So actually, if you look at most recent downscaling methods, what the traditional way of doing it is like to do like a bicubic or bilinear interpolation, and then you pass it through a neural network. But so that just considers the spatial autocorrelation. It doesn't consider the spatial dependencies with the surrounding areas beyond your neighboring cells. So if you consider Kriging, it just considers even the spatial variability, the spatial dependencies to a certain extent based on what kind of variogram you're defining. So in our case, we have a Matten variogram, so that would actually handle the spatial dependencies, not just in your neighboring cells, but also to a certain extent beyond. And after that, it goes flat. So that's what the starting point is, but we cannot only use Kriging because that's still an interpolation and that still doesn't handle the nonlinear relationships that well. So yeah, it's still a linear. Yeah. Yeah. Thanks.